47,000 tokens burned in 8 minutes, and the user saw nothing. 2 LangGraph agents were stuck in an infinite loop because the critic's prompt told it to be thorough and critical with no approval threshold. The article mentions maxIterations, but does not show how to set it. In LangGraph, you pass maxIterations to the compile method to cap total node executions and prevent infinite loops. This is critical for production to avoid runaway token burn. The article mentions MapReduce for parallel subtasks, but does not show the send API. Use send to fan out to multiple nodes concurrently, then collect results with a reducer node. This reduces total execution time when agents are independent. The article uses at LangChain/LangGraph, which is the LangChain integration package. As of LangGraph v02+, the StateGraph API changed. Annotation, root replaced StateGraph, state schema, and send is imported from at LangChain/LangGraph. Ensure you use compatible versions to avoid runtime errors. Let's break down building multi-agent AI systems with Next.js and LangGraph, how it works, and the exact mistake behind that failure. LangGraph is a framework for building stateful, multi-actor applications with LLMs. It models AI workflows as directed graphs where nodes are computational steps and edges define control flow. State carries conversation history and tool outputs through the graph. A single agent with many tools produces inconsistent results. The fix is decomposition. Split the task across specialized agents, each with a narrow responsibility and a clear handoff protocol. LangGraph compiles a graph from nodes, edges, and state. The checkpointer persists state after each node, enabling human-in-the-loop and crash recovery. Keep state minimal to control token costs. Here we define the graph state and the first node. The state includes fields for each agent's output, control flags, and a token budget. The research node calls an LLM and returns the research text along with the updated token budget. The analysis node extracts insights from the research, and the writer node produces the final report. Each node updates the token budget and increments the revision count. The conditional edge decides whether to loop back to the researcher or end. It checks token budget, revision count, and approval status. The graph is compiled with a Supabase Checkpointer for persistence. The supervisor pattern is the most common multi-agent topology. A supervisor agent receives the user request, decomposes it into subtasks, and routes each to a specialist. Each specialist has a narrow toolset and a focused prompt. The supervisor uses structured output to return a list of tasks, each assigned to a specialist. This forces the LLM to produce valid JSON that the graph can parse. Each specialist agent is created with a focus system prompt and a small set of tools. This ensures each agent does one thing well and doesn't get confused. Without a checkpointer, state lives in memory and is lost on restart. Supabase provides Postgres-backed persistence that survives restarts and supports concurrent access. This is the full Supabase Checkpointer implementation. It implements getTuple, list, and put methods to persist and retrieve graph state. Note the use of JSON serialization for state and metadata. High-risk actions need human approval. The graph pauses at an interrupt node, presents the proposal to the user, and resumes with the decision. The state is frozen between interrupt and resume. This React component renders the human-in-the-loop approval UI. It shows the proposal, risk level, and approve/reject buttons. Rejection requires feedback so the agent can revise. Multi-agent execution can take 10-60 seconds. Streaming shows each node's output as it completes, preventing blank screens. Send node-started events before execution to show status immediately. This Next.js root handler streams graph execution events via server-sent events. Each node's output is sent as a JSON event. The stream closes when the graph finishes or an error occurs. LangSmith provides distributed tracing for LangGraph executions. Each run produces a tree of spans. Tag traces with userid, threaded, and environment for filtering. Sample at 10% in production to control costs. This configuration enables LangSmith tracing with sampling. In staging, 100% of runs are traced. In production, only 10% of successful runs are traced, but all error traces are logged. This is the same issue we highlighted at the start. Here's exactly why that happened. The graph had no max iteration cap. Two agents kept debating, each iteration appending to the state and consuming more tokens. Without a termination condition, the loop ran until the token budget was exhausted. The critic agent's prompt lacked an approval threshold, and the graph had no maximum iteration limit, causing two agents to loop endlessly and burn 47,000 tokens. The fix is to enforce a maximum iteration limit. In the conditional edge, we check revision count and token budget. If either exceeds a threshold, we force-end the loop. This prevents runaway token consumption. This is the exact mistake that caused the 47K token burn. Without max iterations, the graph can loop indefinitely. Always set a hard cap on total node executions. Tool selection accuracy degrades above 5 tools. The agent confuses similar tools and selects the wrong one. If you need more tools, split the agent into 2. Each LangSmith trace costs money based on the number of spans. A multi-agent graph with 5 nodes and retry loops produces 10+ spans per execution. At 1,000 daily executions, that's 10,000+ spans per day. Always sample in production. To debug token burn, enable LangSmith Tracing and check the token usage per node. Also monitor state size growth. Test your graph with a low max iterations to verify termination. Let's run through some common interview questions. What is LangGraph? A framework for building stateful, multi-actor applications with LLMs as directed graphs. How does human-in-the-loop work? Interrupt node pauses graph, saves state, waits for human approval, then resumes. Why decompose agents? Monolith agents with many tools fail. Specialized agents with 2-3 tools are more reliable. And a few frequently asked questions. What is the supervisor pattern? A supervisor agent decomposes tasks and routes to specialist agents. How to persist state? Use a Supabase Checkpointer that saves state after each node execution. How to prevent infinite loops? Set max iterations at compile time and check state change thresholds. Let's recap the key takeaways. Decompose agents by capability. Set max iterations to prevent token burn. Persist state with Supabase Checkpointer. Stream execution to avoid blank screens. Ready to go deeper? Up next, getting started with Next.js 16. Installation and project structure, then pages and layouts in Next.js. File-based routing explained, then server components versus client components in Next.js 16 and data fetching in Next.js 16. Server components, streaming, and suspense. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.